Are we live? Oh, we are live. So, okay, finally the setup has done. Like it's a nightmare to set up this mic thing when you have two mics. Well, whatever. So, what are we doing today? Today, we are doing this. So the last time I had this thing. Let us go to there. So last time we did. Okay, so this one is live. Nice. So last time we did this Nade part 4 part. Part 4 part. What the fuck? Nade part 4. In this, I'm trying to write a Zephyr integration module. What this does is that basically I have this this Nade thing, and then the Nade APIs are completely blocking APIs. For example, let me show you the code itself. Okay, so I just copy pasted the actual Nade code in here because it's a simple library. Thing is, I have this fragmentation and defragmentation parts. It's basically transport layer protocol. User pass this data, and this library, all it does is just frag this data and then does the opposite of frag, which is defragmentation, and passes that defrag data, the combined data, to the user via this on-frame callback. These names will have to change because they are based on my previous implementation called frame protocol. You can see the existing code called the frame protocol. So I have to change this. We'll do that later. But the point is, these Nade APIs are synchronous APIs. Means they are blocking calls. So whenever the user call this frag part, it will block the control until the complete data is fragmented, which may or may not take a lot of time depending on how big this data is. So what I want to do in this case is create a basically async part of this thing, and create it as a Zephyr RTOS module instead of a generic async part of this Nade itself, because you can see this Nade this Nade is completely pure C. So to implement async code in C is just a heck of a lot of work, because I have to have those primitives for async code, like queues, blocking on queues, and so on and so forth, right? And all those things are provided by Zephyr free of cost, like already. So that's why I'm going to use Zephyr RTOS for this, and we are doing this. So that's why the designing async Nade. The thing is, turns out this is not a very easy thing to do, not a very difficult thing also, but I mean, you know. So where should we begin? I will start with the design process itself. Like, what is it that we want? Actually, in the previous stream in this one, I already did some thing, but it was like 2 months ago, so I forgot everything. So in this part, let me just do this thing. So in this, why am I writing code in here? Okay, so in here, what I did, I basically laid down some interface called Nade SVC layer, and I don't know what I did there. I just don't actually remember. So I'm going to start over this part, this particular design part. We may or may not write code in this stream, so that's the point to keep in mind. Let's start the designing process. First, I'll have to stop firewall D, and then I'll yeah, this part. This basically lets me share my tablet's screen, which is an Apple one, and you know the cases of Apple things. Screen mirroring. Okay, should not do that. Stop mirroring. Turn on the auto rotate part. Please rotate. And now we'll do the screen mirroring. What is this thing? Who knows? Let's scroll down. Cool. So what is this thing? I don't know. Where should I do this thing? I feel like I should explain this one thing first, because that will give us a quite rich picture. Because the thing is, this inside this there are a lot of things going on in my head right now, and I don't know what to say or not. Point is, I did not document this thing very good yet. So all these malloc and malloc calls in there, they create certain layout of memory, but it's not very clear from the code itself what that layout is. And until we have the layout, memory layout in our head, the mental model of this thing, we cannot reason about the service layer itself, because everything is based on this memory, like who's allocating what memory, uh, who's pointing to what, who's the owner of what, how many, like yeah, from owner part, it's like service layer will basically have queues, and in those queues, how many queues are going to there, is it a send or a receive queue, or is it just a send queue or single queue? So all these things will become very clear, or would say easy to follow, if we first lay out this memory which is being used. What the fuck is happening out there? Wait a minute. I think a cat just declared an act of war outside. Well, whatever. Okay, so layout, yeah. Enough with the talking. I'll already like what 5-10 minutes in. Okay, so the existing holy shit man, ये तो होना ही था मालिक. ठीक है, तो existing Nade, is it visible? Yeah. Memory layout. Like how is it malloc thing laying itself out? So what do we have in Nade itself? Forget about the service layer, just for the time being, the synchronous, the blocking API. What do we have there? So in the blocking API, wait a minute, भैया कौन है रे? So what do we oh fuck, I think I should wait a minute. I'll just do one thing. From now on, I'm going to share these streams on Twitter, so that show that I can have some reach, brother. How do I do this? How do we share streams on this part? And that should show me that I am alive. so alive mean live, and copy link, post. I can go live on X also. Should I do that? What's happening? What's happening is I don't know how to designing. What did I name this thing? Designing async Nade. Basically, I should call it designing async library on YouTube. Links are shortened automatically. Why would you do that? There's an async library on YouTube live. I don't know, not a very catchy name, I would say, but does the work, I guess. Its title is kind of misleading. I'm not designing an async library itself, but some sort of part of it. Well, whatever. Okay, so where are we? This existing layout. So the existing layout is let me show you this thing. So let's start with this fundamental. Okay, I never covered this part in previous Nade streams, but that's that. The thing is, here the user is basically getting all these this Nade interface, and he will pass values onto these, but he will never touch this. It's for the internal usage. So basically this thing will be a private context for Nade, and if we go back into our nade.c, you can see that when user call initially this new thing, Nade new, we are only going to lay out the mallocs only, because this is the matter in hand. So you can see the interface that user passes into this thing. I'm going to use the private ctx and malloc some memory and store a pointer into this. The point is, let's look at this. What is this Nade ctx itself? It's a private thing to the Nade itself, so it is not available for user to read. That's why the private ctx. So inside this Nade context, we have a couple of pointers, basically 2 pointers, a user payload and a packet type. I should also club these into a structure, but that's बाद में करते हैं. So let's just lay out only the pointer part, because this is what the memory what? Well, pointer points to memory, and we are tracking memory, so pointer makes the sense. So the thing is, so when the user calls this new thing, we store malloc into the private variable called private ctx. So if I start from here, I will have this this variable called interface. You can see this here, and type of this interface is this Nade ITF pointer. So I'll write this as Nade ITF pointer, right? And to visualize this, we'll just use some rectangles. So it is nothing but a rectangle, Nade ITF itself, which for all purposes is only have this PRV CTX whose type is void pointer. All right. Now what this does is we are doing in here is we call malloc, and we store that address into this thing, and we malloc a nade CTX, right? So if this pointer will point to some thing which it should not have done that. Man, this is gonna take some time. Maybe I should stop drawing rectangles and just done with it. Yeah, we'll do that. So it will nah, I will not do that. So this thing will allocate memory for something called Nade CTX, and so this is the type of this thing, Nade CTX. So this memory is being allocated, and this pointer is address is stored in this thing. So that's why this PRV CTX points to the Nade structure itself, right? So this is mallocked. So to represent that this is mallocked, I'll somewhere write m, that this is mallocked, right? So inside this Nade, what do we see? If we see there are all of variables in there, all of the fields or the members, whatever you want to call it, and we are going to track these two values. So basically user payload and the packet part. So inside this thing we have a variable called packet, which is of type packet pointer, and we have another variable called user payload, and its type is basically pointer to u8 int. I'm gonna call it just u8, and we should write this thing called another variable is very important, user payload length, which is just a size t. Right, we can close it. So now the thing is these two are pointers, like these two are pointers, so they have to point somewhere, and this is where we are going to track what's next. Next thing is this malloc. This malloc is basically allocates memory for packet and stores that address into this thing called packet. It's a context CTX, which is just a variable to, because this was void pointer, so to have the type information I just did assigned another variable of that type. It does causes a little problem because now I have two variables pointing to the same memory. For example, what does this mean is that I have this CTX variable, this points to the same location this PRV CTX point. So basically two pointers pointing at the same memory, which can cause issues sometimes because how would it cause sidetrack side quest नहीं जाना भाई, side quest में नहीं जाते हैं. Malloc किया this packet, and we'll store that into this packet. This packet is same what we did in here for this malloc. So basically this packet will store an address for this packet type, right? So first we'll create this packet type, draw a rectangle, that would mean we have malloced, and then draw an arrow from this packet onto that rectangle. Clear? Okay, moving on to this part. Right, so this is our packet. It was malloced also, and this points to this packet type, right? And inside this packet, let's just see what is inside this packet is. Inside this packet we have two values, which is one is byte pointer to unsigned 8 and length. So this is bytes, which is u8 pointer, and another is length, which is size t. Yeah, control O. So this thing is done. Next is now this byte, we are doing another malloc, which is basically this byte. But before doing this, that we inside the packet's length, we are storing some value which is passed by user into this variable. So basically interface is passed by user, and inside this it had this value. So let me show you this thing called what the fuck. So this was passed by user, so that's why we need that thing. So essentially what is happening is this thing got value from here, and bytes will point to malloc block, and malloc block would be this many bytes, because this thing and this thing are same, and I'm passing it in here, right? So malloc karte hain. It's uint8 array of, okay, let me just, of length, right? So this is type, its type would not be this, it would be an array, but I'm just notation purposes I'm doing this part. Jikra barudilere marudilere. Okay, and this byte pointer will basically do this thing. Length has got the value already, so this is also mallocked, right? So we have this this thing. So Nade interface, that interface will contain this PR private context, and then this private context allocated memory for Nade CTX, Nade context, and inside this Nade context we had basically two pointers. One is packet, another is user payload. Packet was pointing to another malloc packet, which is byte and this size, and the byte was pointing to another malloc a memory area, which is just this many length. So this chart is clear, right? Now this user payload part is remaining. So the next thing is, you can see inside this is user payload part. Okay, so similarly I'll just create a user payload would also be u8, and its length would be this many lengths, right? This many bytes. So it's called user payload length, which is of course passed by user. Cool. And ये नहीं बनाता कि and this is also mallocked, of course, right? So this is the layout of the Nade, right? So inside Nade, every interface that we create is going to have this layout. I think there are only 4 mallocs. 1, 2, 3, 4. Yeah, 4 mallocs. And you can say I'm not freeing this, and that was intentional. Because if because the point of Nade was that it is going to survive throughout the whole program lifetime, because it's a transfer protocol. So as long as the program is running, it's not going to free its internal like any of this. For example, this final bytes, you can say that, I mean, this final byte is going to be used for packet, and this for user payload. So this is going to be used for fragmentation, and this is going to use for defragmentation. Now this is the layout, memory layout of Nade. How do we fit or how do we design our async code around this thing? So essentially, fundamentally, or in the bare minimum, what the async code does is that it just basically deferred execution for Nade APIs. Nade APIs are fragmentation and defragmentation, and deferred execution means those frag and defrag APIs, which is this frag and defrag APIs, would be executed later in the point of time. To do that, we have to enqueue these calls. So whenever user calls Nade frag, it has to enqueue, and then later on some thread will going to dequeue that element and call. Oh, maybe I did said something wrong. Yeah, the service layer will enqueue the request for fragmentation, and then the thread, which is kind of low priority or not low priority. I mean, it's tricky to make it low priority because it's a transmission protocol, and generally network calls are put on a lower priority because maybe there are some other important stuff is going on. But in this case, it's application dependent. So that's why this have this. Okay, at this point I should just not open this Nade. I should open this service layer. Okay, so these were the APIs that were written in the previous stream, I guess. These two are straightforward. They're just going to spawn some threads for the execution of those enqueues, which is enqueued by these calls. So frag async would enqueue something, defrag packet would enqueue something, I guess, I don't know, and the threads spawned through this API would execute these calls. This is going to create a new SVC context. So let's look at the code of this thing. So here we are. It's like I said, it's a code from previous frame protocol implementation. So in that implementation we had two threads, thread 1 and thread 2. Basically, one was for fragmentation, another one was for defragmentation. I'm not sure how am I going to design this new implementation, SVC or service implementation. So the new API, so let's take one API at a time, and then we'll move forward. This is pretty straightforward, so let's just see what do we have here. And inside this new, essentially it is going to call the Nade, the blocking call, and this CTX is basically supposed to be this. It's a typo, I know. So basically, too much basically is happening in here. Oh, what the fuck? What the fuck? So this so inside this SVC context, I have just another the actual Nade interface. So the idea was, as far as I can tell, is that do this mapping of SVC context and Nade interface on the user end, so that I don't have to write a custom code to manage the mapping. Basically, each context is carrying its own interface. So if we go by this approach, then what do we end up with is basically so the association has happened between this SVC context and the interface. This association has already happened in the user space, and so this call is essentially complete in itself, and I should call this actual my ctx. So this thing is essentially done, this API implementation. Now the next one is this frag part, right? And this is where things get a little bit complex, I would say. How? Well. So let's go by the approach that was done initially. So if each if each CTX, if each service CTX will have Nade interface, and then this Nade interface is going to have basically going to have all these is going to have this memory layout. So this is each interface, like each Nade interface, this ITF, which is this thing. Let me just write it in here. Is essentially the moment you call the Nade new, which like somewhere you would call this thing called Nade new and would pass in this interface ITF, this variable, and it is going to create memory which would look like this, right? So each service context would look like this. So for deferred or for async code, at least I need a queue, right? And inside that queue, just a side quest, a small side quest. When I did this malloc, it allocated this much memory. So basically, this one was a 32-bit architecture. In terms of 32-bit architecture, which is what I'm targeting here, it's a 4 byte, and this is also 4 byte. So 444. ignoring the padding and all. Char 12, basically 12 bytes in here. Is it 8 or 4? I think 4. And another malloc is here, which is just 4 and 4, which is 8 bytes. And this is true malloc. So if I would have instead of a pointer, if I would have, I mean, it's an optimization, no doubt. I mean, it's an optimization. So if I would have done thing like, okay, so this is inside nade.c. Just a little side quest, a small one. If I, instead of writing pointer, if I had done simply this, then I would not have to malloc this part, the packet. Because the Nade context itself will contain a packet, which is basically this rectangle would shift from here into here, and that's it. And similarly, if I club these two, or these user parts, yeah, essentially, like yeah, it would right, yeah. Yeah, so exactly. Let me say it what I'm thinking. Right now, when I put this packet pointer in here, now I have to malloc and create a memory block, which is this one. But if I put it in here, then all I malloc is for this many bytes, this last block. As you can see inside this thing, when I did not create a structure, when I did not combine these related thing, because essentially it is bytes and length, it is also bytes and lengths, right? So this is packed together and separated out. If I pack them together and separate it out, then the layout would also be another similarly, like in this there will be block similar to this, and then this block U8 user payload length would shift in here. So if I, yeah, so essentially that would save me how many bytes? I mean, on paper it seems like it would save, I don't know about compiler and things. This is a 4 and 4, it is 8 bytes, and if I take these 8 bytes and put it in here, which is 4 bytes, so essentially 8 minus 4 is 4. So if I remove this, then I would have a block, this block would sit in here and would take up 4 bytes and 4 bytes, and this one would be removed. So the 8 bytes would be saved. So it's just a pointer, and this thing is predefined. Like at compile time, I know its size. There is nothing variable in here. This is the length which is variable. So essentially, yeah, that's there. This is good. I will club them, and yeah, you never do that, man. If you have a structure in here that you have packed similar data together, then don't, and you are going to malloc, then don't put a pointer. It doesn't save anything. It just creates a mess like this one. Essentially, we'll implement this later. My point is, each service context would look would have an interface which, after calling this new API, look like this. Now, what do we do with this information? So initially I said that how many minutes has it been? It's been अरे टाइम दिखा दे रे लाला 40 मिनट ओके So essentially, basically what I said earlier is I essentially need a queue which would enqueue some elements and then E1, E2, E3, and then some thread will run on this and start executing these elements. Now my point is, now the concern is there are two endpoints for data. One is from the user, which would be my frag part, and another one would be from the hardware callbacks, which would be defrag part. So when user calls frag, it will pass me its entire data, and when hardware calls defrag, it will pass me a single packet. इधर आते ही चीजें बहुत ज्यादा गड़बड़ हो जाती हैं यार. Like at this is where things get complicated, because I really have to optimize for memory, and this queue can only be a homogeneous queue, means E1, E2 and E3 are going to be of same type, otherwise the ownership part opens up. If I put mem pointers in there, then the ownership and all the other Pandora's box gets open up. And when it is going to be homogeneous, then okay, I mean each SVC like each SVC context will have just one interface, and this interface is definitely going to work with the same packet length, right? Point is each interface, this Nade interface, is associated with the one hardware. For example, if this Nade interface is for the CAN part, CAN hardware, then then the packet length that this interface is going to have is the length of the CAN message, which is, let's just say, 64 bytes for FD CAN by default. So essentially the type of this data, this when it is defragging for this particular SVC context, is going to be of this fixed packet. So it solves one problem. And this data that is user going to send when calling frag is also going to be some maximum value which is provided by the user. So essentially my library basically bottleneck by how big user data is. I think it simplifies problem a lot, because in this case now the thing is let's just So I can have two queues for simplicity. For example, this one is for frag queue, and this one is defrag queue. If this happens, then essentially it's this earlier design, which is having two threads, okay, thread create. One is for user data, one is for packet. All right, packet. Or or it's a big or I can have a single queue in which uh, it will have element, and these element will have both the data and the packet. But now the point is this execution thread t t t t this execution thread, how is it going to know which one is put into the queue, whether is it a user data or a packet? Because though both calls, let's just call frag async. Remember, we are for the service for the async part. So async and defrag async. So both of these APIs is going to put data into the single queue, and I mean, I don't know if I should. What the fuck, man? I don't know if I should start with the two queues because the implementation would be simpler, and then I can optimize for single queue. But given how I am designed, I will probably pick the harder implementation, which is having single queue. Then I can put some tag into this. What I'm saying is that each element in this, let's say we are going with this, then each element is going to let's just say I call it q element. Each element is going to have called element tag called tag, and tag and the actual data, right? Data which is either this packet or the user data. Well, I should call this user payload. Use as rpld. And now I have a problem in here, a slight problem. The problem is Let's just say this is data of type this, which, and right now the problem comes that the library has to know, like I cannot create I don't know if I can create this queue at runtime or not. Basically, whether what I need what will I have to do is each of these queue element boxes will have to vary in size depending on how big the user data is. Okay, okay. That depends if Zephyr allows me to create queues at runtime. I think it does. I think it does, but it asks me size of the element. This is the name, size of the element, number of elements, and what is this thing? Ah, great. These are all from previous implementation. We'll have to revisit them. Yeah, exactly my point. That like if I do this, then it is element tag, which is, let's just say, 4 bytes. It's an enum, and then this is a variable pointer, which is again 4 bytes. So the element message size, which is this one, would be 4 and 4 8. So q effectively will get one value and one pointer, which will point somewhere, who knows. And as this element gets pushed, this who's the owner of this memory, so the ownership part opens up. So that's why I cannot have a pointer inside the element. So this has to be an an array which with a max capacity of user payload. Now the problem is this user payload is provided at runtime, not compile time, and I need this information at compile time because C does not allow me to have this. I can use kconfig for this thing and ask the user to inject this value while it is configuring all the other parts of its application, and assuming user is using Zephyr and I'm also using the kconfig, which is essentially Zephyr. Zephyr also uses kconfig and I'm also using kconfig and Zephyr. User is using Zephyr. So I mean, this is not a generic service layer, right? It is specific for Zephyr. It is a Zephyr integration module. So I think it is safe to use keyconfig for this. Like for Nade part, user can simply, it says pure C, so user can pass these values and these max number of packets, or even better, It's I mean you can use kconfig, but the problem is it would be very no very non-ergonomic way to configure these values, because sometime Nade service layer just asking to pass the pointer to the Nade CTX, which is essentially a wrapper for this thing, and inside this it's pure C, so the user will just type values in C, not kconfig. But then on some disconnected level, I'm asking user to provide values through kconfig. It's not a very good design, I would say. So yeah, cannot do that. Cannot have a pointer inside the element. So how do we solve this thing? What is the problem exactly? I can have a tag, no doubt, but I can't have a pointer. And why do I want to have a pointer in the first place? I think I'm missing something in here. Very slightly, but I'm missing. I might have to complete it off stream, because this is going to take some thinking time. A lot of thinking time, I guess. Until then, see you boys. Like I said, no coding today. Ta-ta. Good night.